of this nice result, this law of quadratic reciprocity. Remember this thing, this Legendre symbol. Do I need to keep reviewing this every time? Legendre symbol of n, p, is plus 1 if there exists a y such that n is equal to y squared mod p. So if it is a quadratic residue, and it's minus 1 if there does not exist a y such that n is congruent to y squared mod. So it's this indicator function that signifies, by taking a value plus 1 or minus 1, whether n is or is not a quadratic residue modulo p. And this law of quadratic reciprocity is this really nice result which relates the status of q modulo p to p modulo q. And as I've stressed before, the group of integers modulo p, the group of integers modulo q, and p and q are two different primes, they're two different groups. And from where we stand at the moment, there's no reason to expect any strong connections between the two. So if there's a 50-50 chance of any particular n being a quadratic residue modulo p when you select it randomly, if, so there's a 50-50 chance of q being a quadratic residue modulo p, and equally well a 50-50 chance of p being a quadratic residue modulo q, if they were completely independent, if there was no deeper connections between the two systems, you'd only expect q mod p, the Legendre symbol, to be equal to the Legendre symbol p mod q in what's a little exercise in probability. How often if you flip two coins, how often, what's the chances of them agreeing? It's a half, isn't it? It's 4 possibilities in total. 2 of them are two heads and 2 tails. So 2 out of the 4 flips of 2 independent coins. You'd expect the coins to agree only half of the time, whereas the law of quadratic reciprocity says that they actually agree 3/4 of the time, in a sense. These aren't strict probabilistic things, but it's just a way of explaining that this is actually an interesting result. It's saying that there's a connection much stronger than you'd expect to be if the two systems were completely independent. Okay, because they're equal, so they're either both quadratic residues modulo the other one, or they're both not. That happens 3/4 of the time, because the only time it doesn't, where they have opposite status, is when both p and q are congruent to 3 modulo 4. And a randomly selected prime, every prime is congruent to 1 or 3 modulo 4. And I think I'm right in saying, if you randomly select a prime, it's kind of 50-50 chance it'll be 1 mod 4, 50-50 chance it'll be 3 mod 4. I think. Well, I better be careful. I don't want to say something wrong. But I think the density of the primes in the arithmetic sequence 1 mod 4 as you go up in the integers, I think it'll probably be more or less the same as the density of the primes in the arithmetic sequence 3 mod 4. I think I'm correct in saying that. So anyway, so we have this law of quadratic reciprocity, and moreover, it tells us when there isn't, when they have the same status and when they have opposite status. But the condition is really, really easy to check. Even if p and q are gigantic primes, you just, to divide by 4 is still, one of the quicker operations you can do with a large number. Just divide it and just see what remainder pops out at the end, whether it's a remainder of 1 or a remainder of 3. So it's not a difficult condition to check. Okay. So this is what we have to get to the proof of. Now, what results have we proved about the Legendre symbol? Well, so just scrolling back a bit, we proved Euler's criterion, which is really, really nice. It says the Legendre symbol value, which is going to be plus or minus 1, that is congruent to raising n to the power of p minus 1 over 2. Okay. I won't go through the argument for that again, but we proved that a few lectures ago. And we immediately got some interesting consequences out of that. We immediately were able to settle the status of minus 1 modulo p. We simply raise minus 1 to the power of p minus 1 over 2. And that's either going to be plus or minus 1, depending on whether that was plus, whether p minus 1 over 2 was odd or even, and that, if you see what that means, this index being odd or even just means p being congruent to 1 mod 4 or p being congruent to 3 mod 4. Okay. So a really easy condition to check on the prime p, whether it's 1 or 3 modulo 4, and that tells you the status of minus 1, whether minus 1 is a quadratic residue or not. Slightly trickier was we got a similar result for 2 modulo. So when in our initial examples we started looking at, sometimes 2 was a square, sometimes it wasn't. And from the examples we looked at, there was no apparent pattern, and there was nothing immediately obvious that said, oh, it's clearly 2 is a quadratic residue when it's like this, and 2 is a quadratic residue when it's like that. There was nothing immediately obvious coming off the examples we looked at to say that. And we would have had to look at quite a few examples in order to detect this result. Maybe I should have done that. Got the computer to go through a load of primes and list the ones where it is a residue, list the ones where it wasn't, and we could have searched for a pattern. We might have discovered that when 2 was a quadratic residue, it was only happening in the case where p was congruent to 1 or 7 modulo 8, plus or minus 1. And similarly, it's not a residue when p has the other options, modulo 8, plus or minus 3. Remember, a prime p can't be congruent to 2, 4, or 6 modulo 8 because those numbers will be even. So if we discard the first prime 2, an odd prime has to be either plus or minus 1 or plus or minus 3 modulo 8. So that was the status of 2. That took a little bit more. It wasn't such a quick proof as the minus 1 case. And where we're going to begin today, the first result we're going to look at today, is what we get when we generalize the argument that we went through for proving that result about 2 modulo p. And this is this theorem of Gauss. This again, we see this as another way of evaluating the Legendre symbol. Okay? At the moment, we've got Euler's criterion. Well, the very first way you have of evaluating the Legendre symbol is trial and error. Right? Go through all of the congruence classes modulo p. So take all the possible y's, square them, and see if you ever arrive at n modulo p. That's just the kind of very naive trial and error way of evaluating this straight from the definition. So that result we just looked at, Euler's criterion says, well, we can do slightly better than just kind of blind checking. We can actually go, uninformed checking. We can actually evaluate this number. We can raise n to the power of p minus 1 over 2 modulo p. So that's Euler's criterion. So now this results. This result attached to Gauss here is a generalization of the argument that we went through with 2 modulo p. So we're going to apply Euler's criterion and do what we can with this expression here and get some kind of a decision, extract some kind of a decision procedure out of this. Okay, so what's the decision procedure? Well, this is in the statement of the theorem here. So suppose p is an odd prime, n is not congruent to 0 modulo p, so that just means n is something in the multiplicative group modulo p. So what we're going to do is we're going to look at, remember when we were proving it for 2 mod p, we looked at we looked at 2, 4, 6, etc., all the way up as far as p minus 1. We looked at all the even congruence classes. Well, here we're going to do the same thing, but for n. So rather than look at all the multiples of 2, we'll look at all the multiples of n. Okay, but only the first half of them. Okay. So we're looking at n, 2 times n, 3 times n, all the way up as far as p minus 1 over 2 times n. Okay. Remember, there's p minus 1 elements in the multiplicative group Z mod p. So we're just using the first half, we're just looking at the first half of all the multiples of n. Now, if we look at the standard residues of these, okay, so the standard reduced representative of these congruence classes, see pretty soon, depending on depending on what n is, some of these integers here will soon be greater than p. Yeah, they'll soon be greater than p, so we'll reduce them modulo p. And we'll get the standard small representative of the congruence class. The decision procedure I've referred to here is where we count the number of these residues which come out in the second half of all the residues modulo p. If you think of the integers modulo p, you've got 1, 2, 3, all the way up as far as p up here somewhere, or p minus 1. That's the last residue class. That's the last congruence class modulo p. Remember, we're not including 0 because we're in the multiplicative group, so we're only considering the non-zero numbers. Well, the halfway stage is here somewhere, p over 2. On either side of it are p minus 1 over 2 and the integer p plus 1 over 2. Remember, p is an odd number, it's an odd prime, so these are integers. So here's the halfway stage. We've got the first half of congruence classes and the second half of congruence classes. So this m we're talking about here is the number of congruence is the number of times we end up in the second half from the congruence classes of these multiples of n. Let's picture it's quite a technical result, and the proof is a bit, very kind of detailed and technical. Okay. So some of these early, if n is a small congruence class, from somewhere low down, n, 2 times n, 3 times n, they'll still all be in the first half. So if n was small and p is large, 2 times n, 3 times n will still be in the first half. But after a while, you'll start hitting into the second half of the congruence classes. And after a while, you'll start the multiples of n might go much greater than p. Well, they will eventually go greater than p, so we'll have to reduce those. And we reduce them to a standard residue. So they're either going to come back to the first half or the second half of the standard residues of modulo p. So this m is the count of the number of ones we see in the second half. And the result is simply that this number m gives you the value of the Legendre symbol by raising minus 1 to the power n. Meaning that if n is even, this Legendre symbol is going to be plus 1, and if n is odd, it's going to be minus 1. So it's the parity of this counting number m which tells you whether it's going to be a quadratic residue or not. Is that okay on the statement of the results? Any queries about that at the moment? Okay. To be honest, these results are getting to be the more difficult ones, the more technical ones in the course, the most technical ones in the course. It's, I struggle even myself to get a very, it's difficult to reduce it and explain it in very intuitive terms. But we should at least understand the, the individual steps and, understand what's going on here. Okay. So we're trying to evaluate n modulo p. We're going to take our n, look at all these multiples of n, reduce them to their standard residues. Some of those residues will end up in the second half of residues modulo p. The count of the number of them that do is this number m. And whether that's even or odd is going to give us the value of the Legendre. And it's all based on Euler's criterion, as you'll see quite soon. Okay. So how do we go about proving this? Well, we take the proof follows the same pattern as the proof for 2 modulo p, previous result we looked at. So we take all these multiples of n, and just to kind of coalesce them all together and package them up into one object, we just multiply them all together. Okay, so we produce this very large integer, multiplying these all together. And of course, every one of them has an n in it, so you factorize all those n's out. So you get n to the power p minus 1 over 2. This is p minus 1 over 2 numbers here that we're multiplying together. So if we take out all the n's, you get n to the power p minus 1 over 2. And then, of course, the other factors you're left with is 1 times 2 times 3 times 4, etc., times p minus 3 over 2 times p minus 1 over 2. Well, there you're just multiplying together all the integers between 1 and p minus 1 over 2. So you clearly got p minus 1 over 2 factorial. Okay? So we also had that coming out in the previous proof for 2 mod p as well. Now, of course, we see here the power of n to the power p minus 1 over 2, that's mentioned in Euler's criteria. Okay? So it's the presence of this power of n which is going to allow us to bring in the Legendre symbol. Okay? So we just leave that there for the moment, and we prepare another way of considering all these multiples of n, and we're going to consider another way of multiplying them all together. Okay. This is where it gets a little bit technical. Okay, so all these multiples of n, 1 times n, 2 times n, 3 times n, they're all of this form here, j times n. Some number times n, where j is between 1 and p minus 1 over 2. There's a slight correction to make. Almost tempted to make it here on the page. This minus 1 over here, you should change that to a plus 1 in your notes. This is p plus 1 over 2. Because what we're referring to here is the second half of all the residues here. Okay, so this is how this proof is working. All of these numbers, n, 1 times n, 2 times n, 3 times n, etc., all up as far as p minus 1 over 2 times n, we're going to represent them by their standard reduced residue. But if the residue is falling in the second half, rather than represent it as that residue r, we're going to represent it as a negative of 1 from the first half. Okay? So some of these multiples of n here will be represented by a residue r between 1 and p minus 1 over 2. They're the ones from the first half. So some of these multiples will come out as being one of these r's here, but some of them will be falling in the second half. And those ones we're going to represent as minus r. I think I've written as minus s here. Yeah, minus s, where the s is coming from the first half. So we're representing all these multiples by a bunch of residues with a plus r from the first half, and a bunch of residues minus s, where s is coming from the first half as well. So if you're representing, if one of these comes out as minus 3, it means really it's coming out as p minus 3. But instead of representing it as p minus 3, we're representing it as a minus 3. And this is to introduce the positive and negative signs that are going to give us our power of 1, and so get the result that we want. Okay. So this p minus 1 over 2 here, that should be p plus 1 over 2. Okay, now we need to, we got some complicated representation going on and switching between representation, so we need some nice notation just to clearly indicate this without any vagueness. So in each way, we're going to associate, in this way, we're going to associate to each multiple j times n an element epsilon j sj. Okay. So each of these j times n's gets represented as epsilon j sj. The epsilon j is the plus or minus 1, and sj is a number, is one of these first half of the representatives. Okay. So sj comes from the list 1, 2, 3 up as far as p minus 1 over 2. And the epsilon j is this plus or minus 1, which is indicating whether the original reduced residue of those multiples of n, whether that fell in the bottom half or the top half of the residues modulo p. Okay. So we have epsilon 1, 1, epsilon 2, 2, epsilon 3, 3. So we're keeping the numbers 1, 2, 3 up as far as p minus 1 over 2. We're reducing all the original multiples of n, and each one is carrying a sign in front of it, that epsilon number, which is either plus 1 or minus 1. And now we're going to do the same thing as before. We're going to multiply them all together. But of course, when we're multiplying them all together like this, we can use modulo arithmetic, okay? Because we're saying that j times n is congruent to epsilon j sj, yeah? Just use the same notation. Epsilon j sj, this is a congruence modulo p, and the sj is coming from the first half of the congruence class. Now, I think actually we're going to see all of the SJs get used up, okay? So the collection of all of these SJs, as j runs from 1 to p minus 1 over 2, it will be the complete set of the first half of the representation. Okay, so now we do the same thing as before. Before, we just took all these multiples of n, multiplied them together. Okay, so for the first time, we just worked with an equation. We just factorized out all the n's and saw the presence of a factorial. This time we're multiplying them all together, but we're going to switch to a congruence. So multiplying them all together is going to be, so when we take the product over j of all these multiples of n, this is going to be equal to the product, congruent to the product of all these epsilon j's sj's. So the product of all the multiples of n, before, in the first line of the proof, we reduced it to this, power of n and the factorial. Here we've got the product of all the epsilon j's times j modulo p, where j is going from 1 to p minus 1 over 2. So you again see the factorial, because j is running from 1, 2, 3, 4, all the way up as far as p minus 1 over 2. You've got a factor j there. So you're again seeing the presence of the factorial. And then you're multiplying together all these plus and minus signs. Now, what's the value of multiplying together a string of plus and minus signs? Well, you can immediately forget about all the plus ones. You can just discard those because they don't change the value. So really, you just have to multiply together all the minus signs. And how many minus signs are there? It's this number n, which we referred to in the statement of the theorem, which is the number of times we landed in the top half of the residues modulo p when we reduced each of those multiples of n. Okay? So this is where the number n comes in, and it hopefully comes in as the power on minus 1, as it's supposed to in the statement of the result. Okay? And then it's kind of clear what we need to do. Here's the power of n, which by Euler's criterion is congruent to the Legendre symbol. And we've got this factor here we don't want, but we also see that factor on the other side. And importantly, we also saw it in the previous proof for 2 modulo p. This factorial factor here is co-prime to p. So it's invertible modulo p. So here it is on both sides. If it's an invertible factor on both sides, you can cancel it. Not by dividing both sides by that integer, but properly multiplying both sides by the multiplicative inverse of that integer. That factor p minus 1 over 2 factorial is invertible modulo p, so it can be cancelled from both sides. So we get our power of n is congruent to this power of minus 1. But the power of n by Euler's criterion is congruent to the Legendre symbol. The Legendre symbol is plus or minus 1. The power of minus 1 is plus or minus 1. So if they're being congruent to each other modulo p, they have to actually be equal to each other. So we get our final result, just a straight equality here. So that's that. And this is actually going to be a stepping stone. So we've proved it now, this result of Gauss. And this is going to be, we're going to build on this. And this, together with another preparatory result, will allow us to get the proof of quadratic reciprocity. Okay. Let's see a little example of this before we leave it. Let's just test it out, see if it works. Any questions about the proof, first of all? Now it's a tough read, all right. It's quite technical. There's a lot of indices and plus and minus signs flying around. But you know, this is the real deal. This is you know how difficult and technical number theory can get. It gets a whole lot more, you know, as you go on in it. But you should definitely see, like, the techniques and the ideas we were using there were very much the ones that we used in the proof of the result for 2 modulo p. Very similar ideas being used. So it's kind of a generalization of the argument that we use for 2 mod p. You know, as I said before, we could have kept going, do a separate result for 3 mod p, a separate result for 4 mod p, 5 mod p, etc. But we just have an increasing family of results getting more and more complicated all the time. But this result, due to Gauss and bringing in this idea of counting the number of times you land in the second half, this being that number m there, that's going to be the route to proving quadratic reciprocity in the end. Okay, so let's see if we can apply this. I think some of the tutorial exercises ask you to apply this method to calculate the Legendre symbol. Now to kind of see it properly, we need to choose a moderately high prime. Let's go for 13. It should be high enough to see the thing happening, and it shouldn't be too high to take us all day, and so on. So let's test. So we want to choose some number which isn't obviously a quadratic residue. So we don't want to test if 9 is a quadratic residue, because we know already 9 is the square of 3 and so on. So let's choose something different. Let's say 5. Okay. So is 5 equal congruent to y squared modulo 13 for any y? This is the question. It's not obvious. We don't know. Maybe it is a square. Maybe it isn't. So we want to evaluate 5 mod 13, the Legendre symbol, find out whether it's plus or minus 1. So what we're going to do is we're going to set up all these multiples of 5. So we're considering 5. So we have to go 5, and we're going all the way up as far as p minus 1 over 2. P minus 1 over 2 is all the way up as far as 6. So we're going from 1 times 5 all the way up to 6 times 5. We're going 5, 10, 15, 20, 25, 30. So we're dealing with those 6 integers. 5, 2 times 5, 3 times 5, all the way up as far as p minus 1 over 2 times 5. P is 13, p minus 1 over 2 is 6. And we want to reduce them modulo p. So we're reducing modulo 13. And we're looking at the standard representative we get. Well, 5 is already reduced. 10 is already reduced. Now we actually start reducing. 15 is 2 modulo 13. 20 is 7. 25 is 12. And 30, what is 30? 4? 26 plus 4. Okay. So just to visualize it, here are all the congruence classes modulo 12. Here's the midpoint, the cutoff, p over 2, 6.5. So we're looking at these residues, and we're seeing how many of them are in the first half and how many of them are in the second half. Well, the 5, 2, and 4 clearly live here in the first half. But the ones we're interested in is the other ones. The 10, 7, and 12 are coming from the second half. Okay. So our m, this number m, is 3. Yeah. So it would seem that the Legendre symbol 513 should be equal to -1 to the 3, so it should be minus 1. So the answer to this question should be no. There does not exist a y such that 5 is congruent to y squared modulo 13. Is that true? Did I do it right? Did I make any mistakes? Legendre symbol, command and sage. XP, so just go 513. So I should be seeing a -1 here. Phew, -1. Or you could do for n in the range, for n between 1 and, now you only have to go up as far as the halfway point is 6. We'll look at modulo n squared 13. Yeah, so these are all the quadratic residues, modulo 13, 1, 4, 9, 3, 12, 10, so we don't see 5. Okay. So, and to do that out, I was just following the concepts in the proof, looking at all the multiples of 5, reducing them, modulo 13, and then figuring out which ones are in the second half. So just to help indicate what was going on in the proof, when we looked at this. So if you get onto Sage, so I didn't know the command for Legendre symbol there, for instance, but I guessed it was called something like Legendre. So when you start typing an initial part of a command and you hit the tab key, I think it's like that in MATLAB as well. You have this tab completion. It's very similar, very common thing in computer systems. Type the initial part of the command, hit tab, and it gives you the possible completions of it. And one of those is obviously the correct function, Legendre symbol there. Yeah, so you remember in the proof we had this thing which was difficult to state here when we were bringing in these epsilon plus and minus signs. So in this case, what that would have been, you see here we have the top set here. So that set indicated on line 8.57, that's just this set of values here, 5, 10, 15, etc. up as far as 30. Then we would be representing it as so the 5, so we would be representing it as, so we're plus 5, but the 10 was in the second half, so that would have to be represented as minus 3. So the epsilon 2 was minus 1. The 15 reduced to 2, that was in the first half, so you'd represent that as plus 2. The 20 reduced to 7, that would be minus 6. 25 reduced to 12 in the second half, that's minus 1. And the 30 reduced to 4, that's in the first half, so it's plus 4. So that second set there is this set here in 8.5. You see, you do indeed have all the numbers in the first half, 1, 2, 3, 4, 5, 6. And they all have their associated plus and minus sign. And there's the 3 minus signs. 3 minus signs introduced because those were the residues that were in the second half, so we dragged them back, gave them a minus sign into the first half, so we could multiply them all together, generate that p minus 1 over 2 factorial, which would cancel it from both sides, and we'd just be left with the minus 1 to the power of that number 3. Okay. So, when you actually look at a particular example, it's all just basic arithmetic, but it's just describing it in general and discovering the general patterns that are happening for every possible input to the problem. That's where the difficulty is, I guess. Okay. Any questions about that so far? Any clarification I could offer you in that example? I didn't get that cap. Yes, go on. Question.
Why from 5 to 30? Why not more?
Well, why not more? Well, if we were going... Yeah, so the reason is that if to go any further, we wouldn't get any extra information. We went up as far as the halfway point, p minus 1 over 2. If we went any higher, so if I started thinking about 7 times 5, which is 35, which is the next one. Well, you see 7 times 5, see 7 is minus 6. So this is going to be congruent to minus 6 times 5. Now what's 35 modulo 13? 9, isn't it? 26 plus 9? That's congruent to 9. So I've already seen in 6 times 5, I've seen 4. So I know that minus 6 times 5 is going to be congruent to minus 6. And of course, minus 4. So this 6 times 5 came out as plus 4. So the minus 6 times 5 is going to come out as minus 4. Of course, those two are congruent. So, and if the plus 4 lived in the first half, the minus 4 is going to live in the second half. So this pattern of where these residues fall, whether they fall in the first half or the second half, if I go through the rest of the multiples of 5, like you asked, why don't we look at the other ones? We're just going to see an exact repetition of that, flipped. Whereas in the first half, we see m residues up here, and p minus 1 over 2 minus m ones down here. In the second half, it's just going to be completely reversed. So we're not detecting any new structure or any new phenomena. Okay. Where the residues fell, whether in the first half or the second half, can be completely deduced from where they fall for the first half of the multiples. So it's basically the idea that if you understand what's happening with x in a multiplicative sense, remember we're inside this multiplicative group, we're talking about products and looking at square roots and so on. If you understand what's going on with x, you probably understand what's going on with minus x. That's the kind of basic, like if you know how to factorize the integer x, you automatically know how to factorize minus x into integers. It's just got an extra minus 1 factor on it. If you know how to take the square root of x, you know how to take, well, there won't be a square root of minus x. Yeah. If you know what x squared is, you automatically know what minus x squared is. If you know what x cubed is, you know the cube of minus x is just minus the cube of x. So once you know about a positive thing, you automatically know about the negative thing in any kind of multiplicative question about it. Okay, because you've just got an extra factor of minus 1, and that's kind of what we're seeing. There. Okay. Okay. Now we're not quite ready to jump into the proof of quadratic reciprocity next. We've got another preparatory result to look at, which is, again, more notation coming in, but is a different way to calculate this m, a more efficient way to calculate this m. At the moment, the way I calculated it in that example is I had to look at all the p minus 1 over 2 multiples of n. I had to just figure it out and look at where the residues fell. Whereas here, it's just a slightly different way to calculate it. Okay. So in the next lecture, I think we'll quickly look at the proof of that. I might just look at the statement of that. The proof is maybe a little bit difficult to digest straight away after that one. But in the next hour, we'll look at the statement of this, I think, and then go on and look at another application of quadratic reciprocity as well. So I might postpone dealing with the full proof of it till next week or the week after. Okay, we're going to go through this other preparatory result again, which gives us a different way to calculate m. And then quite confusingly, the whole well, not quite confusingly, quite interestingly, surprisingly, if you look forward to the actual proof, the whole thing turns out to be a kind of a geometric argument in the end. Or not really geometric, it's more a kind of a combinatorical argument. We're going to be counting points inside a rectangle in order to prove quadratic reciprocity, which is quite surprising. Why are we suddenly drawing diagrams and counting dots inside the number theory? So that'll be interesting to see when it comes. So we'll probably do that next week, or if John is taking some, we'll still probably do that next week. So in the second hour, we're going to do more practical stuff. Show another application of quadratic reciprocity and some other interesting results. Yeah, we'll do that. Prove some more interesting results about infinite collections of primes using quadratic reciprocity. Try to persuade you of its use before working our way through all the technical proof of it. Okay. So it's 9:45 now, so we can have a coffee break now, and I'll meet you downstairs in the next room at 10, and we'll look at some of these interesting applications.